Well, I've got my new direct drive rotary motor here from Genesis. Here at Copley, they call it the Jesse motor. It's got the 44 poles, 22 electrical cycle, magnets, and coils inside. So it's they sell the components and they also put it together with bearings and feedback devices. So the motor power is connected UVW with earth and shield. Really nice braided shield here, which you can bond to earth. Um, Running it here with a Xenus compact, 7.5 amps continuous 15 peak. It's pretty good for most of these motors. This is running on 120, but you can also run it on 240. This motor would be perhaps the 240 volt motor. Doesn't go very fast. If you're looking for 6,000 RPM, this is not the kind of motor you'd use. I think the top speed is around 600 RPM, given 120 or 240. And it's got a lot of torque though, so it's wound for torque, which is great because if you're doing like a SCAR robot or something, you can put your arms on here and tune it up. The feedback device, I like this M12 connector, and this one has a BSC 21-bit. It's pretty standard, absolute single turn. They also have incremental encoder with Halls, depending on like if it's a scanning application and you need precision while you're moving, maybe it could be a little better. But I think this 21-bit, like 2 million counts per rev, is pretty darn good resolution. I've got it down to about 0.1 degree move and settle. And so I'm predicting the first application would be sort of a robot arm point-to-point move. So I've got it tuned up for that. The feedback is connected to the Copley here, clock and data for the BIS. I'll go through the configuration. I got my 24 volt Keep Alive. This motor has a brake option, so the wires are available for the brake. There's also a temperature sensor. You probably don't want to hit 200 degrees Celsius, so maybe shut down somewhere before that. Perhaps the feedback device could do 110, not not minus 40 or anything, unless there's heat generated by the motor. Anyways, the drive's all configured with the stow, and I'm using the Copley serial adapter. And let's take a look inside of this motor here. It's coils, right? And they're tightly packed in, 44 poles or 22 electrical cycles, magnets. You got your bearings, optional brake, and feedback devices. This application is showing it used in a Delta style robot, sort of direct drive Delta robot. So plenty of torque. The speeds don't have to be 600 RPM in this type of application. So that's well suited, a motor well suited. Their webpage has the resources. They put the information about the motor right online here, which is kind of nice. You can get the specky stuff. 1830B, you can see the voltage, and then the current amps RMS times the square root of 2 for Copley, so hence the Xenus compact with 7.5. And there's some information in the data sheet about the motor, so they have the data sheet online here. Same specky stuff, inductance, resistance, all the good data you need to configure a drive, nice speed torque curves, and ordering guide. And the manual has more details. I saw information here with some help from Sam on finding the cable pinout. And so this is kind of a standard M12 connector. This is on the motor, and you got your different types of feedbacks here. I'm using the BSC clock and data. There's also incremental encoder with Halls and sine cosine. Anyways, yeah, there's the pinout for the motor power. And here's the pinout for the feedback devices. We can see the wire color situation here. So to make up the cable, I put together just a little note with the wire colors. So on the cable is the female, on the motor is the male. You can look at pin 1, which plugs in to here, but the wire colors are such. For data, S and S not, you've got green, green, white, and for clock, you got brown, brown, white. The shield should be connected to the frame. It's connected to the motor case at the feedback end. I don't normally like to do that, but there's no problems here. I got a good path to earth for the motor case, so we seem to be good. We've got some length of cable here, so that's a good test. And you got your clock in on XX naught, and you got your plus 5 volts going to the U, and the ground is the 0 volts here, so plus 5 with respect to ground. If you did have the sense wires, you could double up the wiring. This one has says no connection, but the wires are populated, but they don't go to the sense. So we could probably use those wires if we had to double up for extra long. So just keep that in mind. Long distance transmission, you got to make sure you still have 5 volts when you're down at the feedback device. So let's take a look at configuration with CME. Basic setup, it's a brushless rotary motor. You've got BIS-C selected here, primary feedback, 21-bit. We don't need to downshift. We're not going that fast. But if you had more counts and you needed to go faster, you'd have to downshift. 2.5 megahertz frequency. This is spot on for this device. I just used the default settings for the configuration of alignments and order. This is just like a Renishaw, so standard configuration. And of course, in a position mode, we update at the position loop rate. We don't ignore the feedback. We fixed the cabling, grounding, shielding problem. So watch out for an occasional CRC error if you're arc welding or in a lightning storm. If you have a brake, you can set the time to stop. Maybe turn the brake on at 1 RPM, depending on your mass, and give it 150 to 200 milliseconds for brake delay. I'm in a position mode doing COE, CAN open over EtherCAT. This drive can also do Ethernet, EIP, Modbus TCP, TCP IP. Anyways, no changes there, so I'll just cancel. And then we start with the motor data. It's a Genesis. There's the winding number. The B17 NA is the BIS-C, 21-bit, 44 poles. Hefty inertia, but 10-to-1 ratio is kind of nice, so that's a big inertia you can hook up there. Huge peak, pretty large, continuous. It might be a little bit different at speed, so just check the specification on that. We don't want to over torque high speed all the time. Torque constant, it gives it to you in Newton meters per amp RMS. So you just enter it here and you can see and then the volts per radians per second. It's the same value for radians for Newton meters per amp peak, volts per kRPM. There's the resistance. I measured it. It's really that. 13.9 millihenry is pretty good. Calculate initial tuning parameters, and that'll save the flash. For the current loop bandwidth, we can check out. I did a little bit of tuning. I cranked it up, manually tuned it, and then backed it off like 10%. I didn't need 1.4 kilohertz of current loop bandwidth. I like about a kilohertz, so that's pretty good. Nice tuned by a human. So there's the continuous current of the motor. You can do greater than continuous for a little bit of time, given the I squared T, and this drive limits us to 15 amps, so almost 3 times the continuous is a good number. I set the velocity limit to 600, which is kind of the speed limit there, but we're going to go less than that. And I cranked up the gains for VP and VI. I used a lot of integral to get to the last count. I wanted to get down around 0.1, so 58 counts out of 2 million, so less than 0.1 degree with that resolution. And I turned off the feed forward term because this is going to be for a point-to-point type application here. So I'd like to see it move and settle. So you can go through, tune the velocity loop like you would normally do. And I moved the filter out, the V loop. I pulled it in case I had a large inertia, but I seem to get a little better tuning if I push it out. It's subjective. I'm no load. If you have a load, you might want to bring the pole in. But no load, I moved it out, made it a single pole, then applied, and cranked up the gains till it buzzed. And boy, this thing buzzed really loud, very scary. But just cut the gain in half and the buzzing goes away. So this is a nice safe value. Twice that will buzz, half that won't. Buzzing goes away. For one distance, one rev, it's 2,097,154. And I got the scope configured for following air, current, and in motion. So we can make some moves. We can see it moving back and forth here. So it's a single turn, distance, there and back. Mounting is here, and mounting holes here to hold it to the frame. So we have a velocity profile hitting 120 RPM. So it takes about a second to make the move, and you can see the settling is really good. The other thing that's interesting about this motor is the feedback device is 21-bit, and it's pretty good, plus or minus just a few counts, maybe plus or minus 2 counts. So no special cabling, grounding, shielding here. I just hooked it up on the bench. You should make sure all cases have a path to earth. You should make sure all shields have a path to earth, maybe bond the motor power wires. But without any precaution, this encoder seems to be pretty immune. So we get nice feedback and move and settle at the end of the move. It settles right away. So this is good for point to point. Don't wait around. You're going to slide right into position. All right, so other features that are interesting. Homing, there's absolute immediate home. So you go to your desired position. If you want this to be 0, you put a minus in for offset, do absolute immediate home. Give it a little jog here. I'm going to run out of time, but the control panel is useful to see what mode you're in. And on the input-output screen, active low enable on pin 1, and motor temperature sensors turned off. We're using I2T. We can measure the motor's RMS current over time. Maybe 5 years from now, the RMS goes up and we have to service something, but the bearings look good. I'm sure this motor is good quality, made in North America. The price is really good too. So I've seen, these motors cost thousands of dollars. So it's less than a few $1,000s, that's for sure. Some of the other ones seem to be a bit pricey, but it's the nature of the direct drive motor. Lots of magnets in there, winding the coils and whatnot. All right, well, thanks for watching.